as data flow analysis, which is problems with the with computed jumps, right? If you need data flow analysis to solve computed jumps, but you can't. So this is sometimes called set use analysis or def use analysis, or definition use analysis. I've heard there is also another statement of def use analysis being related to test coverage, but this is not related to that. This is something different. So for every instruction in the procedure, a node is created. If a variable value is set in a given node, then an outage is created to the node containing the instructions in which the variable value is used. So directed edges are from set to use, which is the set use analysis. So a set would be, you know, move 42 into AX. That you're setting AX to be something. A use is add BX to AX. As I say in this third bullet here, the use is actually also a set because once you're done with this instruction, the value of AX is changed. So that will stop the set from here, and we'll start a new set here. So if you wanted to do analysis on it, you don't have to go back to stuff that doesn't relate to it. All right. This is kind of related to the computed jumps thing, right? These are kinds of instructions that are generated by exception handlers and function pointers in C. So unfortunately, like I said before, you can do some interpolation and figure out exactly, you know, what a compiler may be meaning by this if you know exactly where it was compiled from. But doing a general case does not work very well. Because data flow analysis does not know that this is actually this. It just knows that this is BX. Right? And I think I flipped these, but that's okay. So now control dependence. It's a graph that represents reachability within an application. Can you get something from something else? Will setting this value cause this, well, that's set use, but will that cause, you know, an if statement to go into a different place? You know, that's kind of reachability. So for every conditional statement, a node is created and a true out edge is added to instructions reachable only if the statement is true. The same is done for false. That's a little unnecessary in binary executables, right? Because there's no real false jumps. You just jump if it's true, and then it just falls through if it's not. So you can kind of think of it as the same thing. Because of the lack of structure, this can be very difficult to generate. You know, it's nice in, you know, source code. You have nice little curly braces to show you exactly where things are happening and what code is affected by what code. But in binaries, you don't have that, and so you got to do a whole lot more finagling to get the analysis to be correct. Oh yes, and if you combine the CFG, the control flow graph, and the control dependence graph for the entire application, that can lead you to dead code analysis, which can show you where, hey, we can chop this code out of the binary, and it will, because it will never be executed anyways, which is how compilers do a lot of their, well, some of their optimization. So if you combine the flow dependence and control dependence graphs, this is the program dependence graph for a procedure. So now we can do procedural slicing, slicing of, you know, different functions. However, this is not sufficient because we do need to know everything that is affected by the code that is detected. So it's not really worth just knowing what effects in the function it's in. System dependence graph is a combination of all the PDGs in an application. It's relatively simple. It makes a lot of sense. It's just kind of an extended PDG. You just create out edges from past parameters into the function where those parameters are used. So that's your set use. And out edges from the return value to where they're being used in the column. So Oh, another note. In system dependence, it's also where you would, you kind of need, because of the way global variables work, right, you need to essentially make them, put them in every single program dependence graph that you have, because everything can use a global variable. Registers kind of that way as well. So there's a lot of trickiness to the binary side of this, but pretty cool. So, a slicing example. We got a little application here that doesn't actually do anything. It's just some forced control flow. You know, moves down here. If it's less than, which it will be, jumps down here, sets it equal to, jumps back up, and then it's not less than, so it jumps to the end. So, this is the flow dependence graph for this particular set of instructions. Now you can see, just from this, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. You can kind of think of it as 9 nodes. And 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So there's, just for this tiny little program of 8 instructions, there's quite a bit to be had. So this takes up a lot of space in memory if you don't do it thinking to not take up space in memory. Right, so essentially this means taking a look at this node, right? You're moving 5 into AX, so it's set here, so you're using it here in this add. You're also using it in this compare. You're using it in this move here, which sets a new thing for BX. And so that's why BX is pointing here, and BX is pointing here. But BX from here is not pointing here because this overlaps, because BX gets reset here, so it does not point from there to there. I'm going a little fast on it. Is there any questions about anything? Sorry. No. Control dependence graphs. Right. So we have. This is a little simpler to read. Essentially, every instruction that can be read, that can be gotten to from enter, just has a directed edge to it. And the biggest change here is this jump to my label, which is here. And that is only accessible if this is less, right? Oh, another thing to point out from the last graph, sorry. About this flag, right? Compares and jumps are 2 separate instructions in assembly language, so, or in machine code as well. So when you have a compare, what actually gets done is flags are set, and then those flags are checked whenever a jump is called. So you also need to keep track of the flags in assembly language. Yet another hurdle. So this is the PDG, which is just a combination of the flow dependence and control dependence graphs. The blue is from the control dependence. The black is from the flow dependence. Nothing much else to say there. So there are no other procedures in the example I gave, so it's already a system dependence graph because there is no other functions, there's nothing else, that's all there is. But if we replace add with a function procedure, then the SDG would be created as following. The call has directed edges to enter, push, and push, right? Because those are your parameters passed when you're using assembly. So this particular portion is just the PDG for the function of the add function, which uses add, but we'll talk about that. And then this is the return value that's being used in the caller. So you have a directed edge, sorry, from there to there, and the rest of this is just normal control dependence. So if we want to do a backward slice on add AX BX in this example, which is this particular node right here, first we follow